Dear students, welcome to today's lecture. And we have reached section 5.4.1. And basically we go to the multidimensional case. So we will generalize the statements that we have seen in the previous chapter and in the previous sections to a multidimensional setting. So, and we will end up with the fundamental theorem of asset pricing. So we start with a two-dimensional version of Girsanov's theorem, and that is theorem 5.4.1 in the book. And essentially, if we look at the proof and all the statements that we need, we can really generalize the one-dimensional proof, the one-dimensional statement in a natural way to the two-dimensional case. So let's again start with the setting. Let omega fp be a probability space. And now we have Wt, which is a vector valued process, and it consists in the two-dimensional case of W1t and W2t, t greater equal to 0. And that is now a two-dimensional Brownian motion with the filtration script ft, and little t is between 0 and capital T, where capital T is a fixed time. And we have an adapted process, theta, also vector valued, consisting of theta 1 and theta 2. And again, 0 less or equal to little t, less or equal to capital T. And that is the adapted process. And then we define our Z process, like we know it in the one-dimensional case in a natural generalization. It's e to the power minus the integral from 0 to t of theta 1u dw1u minus the integral from 0 to t theta 2u dw2u minus 1/2 the integral from 0 to t theta 1 squared u plus theta 2 squared u du. Now this can also be written down in a vector valued fashion, and the book does that. So that is then an inner product of theta 1 dw1 plus theta 2 dw2 with a minus sign in front. So that is an inner product, and then we would write it like the book. It is zt is then e to the power minus the integral from 0 to t of the inner product of theta u, the vector value theta u, with dwu minus 1/2, and then the book writes this as a norm. So that is the integral from 0 to t of the norm of theta u squared. And so this you can see as the norm of theta u squared. So that is the exponent here. And of course, we also have this W tilde process from before, and W tilde, the generalization to the two-dimensional case would be that W tilde t is equal to Wt plus the integral from 0 to t theta u du. And notice that these are vector valued processes. So this has a W tilde 1, and that's equal to W1t plus the integral from 0 to t theta 1 du, and it has a second component, W tilde 2t, it's equal to W2t plus the integral from 0 to t theta 2u du. So this is a vector valued notion. Now, again, we assume that integrals exist, and in this case, that means that in expectation, the integral from 0 to t of theta 1 squared u plus theta 2 squared u times zu du is finite, it exists. Okay, we just continue in the fashion that we know from the one-dimensional case. Then we use the notation z is equal to zt, so we can use z safely and we mean zt, and we define the measure change. We have a p tilde a, and that is the integral over a of z dp. So that is like we know it from the one-dimensional case. And then we have the following in our theorem, and remember we are dealing with a theorem here, the two-dimensional Girsanov theorem. So if this is all satisfied and assumed, then we have the following. First of all, the expected value of Z is equal to 1. And in fact, that implies that ZT is a martingale under P. So we also always need to tell under which measure, under P. Secondly, that W tilde T, 0 less or equal to little t less or equal to capital T, that is a two-dimensional Brownian motion under P tilde. So here we have P tilde. And the proof of this, the proof is very similar to the one-dimensional case. And we do it in several stages. We start first, we look at the exponents. So let's look at the exponents to be sure. We look at the exponent. Here you see minus the integral from 0 to t theta 1u dw 1u, and the same term with theta 2. And we have this term. So we consider the exponent, and we call the exponent in the one direction x, and in the two direction we call it y. So what we are doing here is we have an x part of the exponent, and because we want to show that z is a martingale under P. How did we do that? Well, we did that with the Ito-Dublin formula. So we are going to find a function, and for that we always looked carefully at our exponent. And now with the two components in the exponent, a one component and a two component, we will be using two stochastic processes, xt and yt, where xt is the part of the exponent in the one direction, so minus the integral from 0 to t, theta 1u dw 1u, minus 1/2 the integral from 0 to t, theta 1 squared u du. And now we have also, of course, the same part in the two direction, and we call that y. Yt is the similar process in the two direction. So the integral from minus the integral from 0 to t, theta 2u dw 2u, minus 1/2 the integral from 0 to t, theta 2 squared u du. And of course, we also have the differential form of these two. And you remember how they look. They are helpful when we look for the martingale. We look for Ito processes, you remember, and we look for the Ito-Dublin formula. So let's also present the two processes, the dynamics of the two processes in differential form. dxt is minus theta 1t dw 1t minus 1/2 theta 1 squared t dt. And in the second direction, dyt is minus theta 2t dw 2t minus 1/2 theta 2 squared t dt. These are the two that we will be using. These are the two that we use in our Ito-Dublin formula. And you can think of this, right? Z t is e to the power xt plus yt, right? So we see something like e to the power x plus y appearing for our Ito-Dublin formula, and the dynamics for x and y for the two exponents are also important. And again, if we can show that C is a martingale, then C, the expected value of ZT is equal to the expected value of C0, and that is equal to 1. And that is exactly what we need to prove in the first statement. So we will apply the Ito-Dublin formula on the function fxy is e to the power x plus y. Remember, z in this case, zt, is e to the power xt plus yt. And of course, we need the first derivative and the second derivative and the mixed derivatives. And we know them all. They are all equal to f. Yeah? Fx is equal to fy is equal to fxx is equal to fyy is equal to the mixed derivative fxy, and they are all equal to f. So we can substitute this in our formula. And this is the two-dimensional Ito Dublin formula that you may remember from before. Zt is equal to f of xt and yt, and that is, in this case, e to the power xt plus yt. And now using Ito Dublin, that tells us this is equal to f at x0, y0 plus the integral from 0 to t of fx dx plus the integral from 0 to t of fy dy plus 1/2 the integral from 0 to t of fxx dx dx plus 1/2 the integral from 0 to t of fyy dy dy plus the integral from 0 to t of fxy dx dy. Well, this one will cancel out, that I have just explained you. If we look here and we look at the rules of differential calculus, we say dx dy, that will be a dw1, dw2, and these are independent Brownian motions, that is equal to 0. And then we have cross variations that are 0 and dt squared terms that are equal to 0. Dx dx is a minus theta 1, so minus theta 1 dw1t times itself. So that is, in fact, theta 1 squared dt, and dy dy is theta 2 squared dt. The other terms again cancel out and are equal to 0. So we substitute all of this. For this, we substituted dx, for this the dy, for this theta 1 squared dt, and for this theta 2 squared dt. And then we see that there will be a dt term here, 1/2 theta 1 squared dt, and that will cancel out with this one. There's a minus sign in front here. And the same here, we have minus 1/2 theta 2 squared dt, and we will also have that here with the ZU. So fx0 y0 is equal to 1. And when we write it all out diligently, then the only thing that remains is minus the integral from 0 to t, zu theta 1u dw1u, minus the integral from 0 to t, zu theta 2u dw2u. And this is a form that we like. Of course, we recognize here two Ito integrals with respect to the Brownian motion, and that is always good. We see here a sum of two Ito integrals, and that means that we have a martingale under P, dw2u dw1u, and martingale under P, and this implies that in expectation z, the expected value of z, and that was of course the expected value of zt, by means of the martingale condition, that is equal to the expected value of z at t0, z0, and that is equal to 1. So that is the proof of 1. Yeah, so 1 is this. In expected value z, the expected value of z is equal to 1. And let's recall the second statement. The second statement was that w tilde t, 0 less or equal to little t less or equal to capital T, is a two-dimensional Brownian motion under P tilde. And how do we do that? How did we do that? We did that as follows. We will use the two-dimensional Lévy characterization and for Brownian motion. And well, there are some things that are easily checked. First of all, w tilde 1, 0 is equal to w tilde 2, 0 is equal to 0. And there are some other terms. You recall continuous paths. The quadratic variation should be equal to t. The cross variation should be equal to 0 in the two-dimensional case. And we should show that it's a martingale. Now, the continuous paths are just standard. W tilde it for all time has continuous paths. For I is 1 and I is 2. No reason to not assume that the individual components have continuous paths. Also, regarding the quadratic variation of W tilde I, for I is 1 and I is 2, we can easily show that that is equal to the quadratic variation of Wi, and that is equal to T. And the cross variation similarly, we can, for these two, we can just use the rules of the differential rules to show this. So the cross variation, W tilde I, W tilde J, for I not equal to J, that is equal to 0. And then what remains to prove is that both W tilde 1 and W tilde 2, T and little t between 0 and capital T, that these are martingales under P tilde. Yeah, when we have that, then we know that these are Brownian motions, right? That is the essence of the Lévy characterization. Now, how did we do that? Well, remember, we looked at W tilde times Z. Yeah. So in the proof essentially follows the same steps as in the one-dimensional case. So how did we do that in the one-dimensional case? Maybe you recall. We first claim that W tilde IT times ZT, where little t runs from 0 to capital T, that is a martingale under P. Yeah, that is the first step that we take. And how do we do that? Well, we see a product here. So we will show that by means of the Ito product rule that we're dealing with Ito processes, right? So remember what we have seen. dzt is minus zt theta 1t dw1t minus zt theta 2t dw2t. That is one thing that we have seen. And of course, we have these two components. dw tilde 1t is equal to dw1t plus theta 1t dt. And the same for the second component, dw tilde 2t is equal to dw2t plus theta 2t dt. And this we can substitute into the Ito product rule. So the Ito product rule, by that we get the dynamics of W, for example, W tilde 1t zt, and we can do the same for W tilde 2t zt, but we only do it for W tilde 1t zt. And you remember how it was. So here we have it, the whole bumps at once. So this is zt dw tilde 1t plus w tilde 1t dzt plus the differentials of both dzt dw tilde 1t. And then we can substitute the individual terms. For this one, we substitute this one here with a 1. And for this one, we can substitute this one here, and we also need both here. So let's do that. We just copy zt, that's equal to zt times dw1t plus theta 1t dt, plus, and then we get the second term, w tilde 1t, and then we substitute dzt, and that is minus zt theta 1t dw1t minus zt theta 2t dw2t. And we close the bracket. And then we have the cross term here, right? So the correlation type term. So we have dzt, that is again minus zt theta 1t dw1t minus zt theta 2t dw2t, and we multiply it in this case by dw tilde 1t. So we multiply it by dw1t plus theta 1t dt. So let's see what we get. Well, we get here, we get as the first term here, we get zt dw1t. That is here. Then we have zt theta 1t dt, that is over here. Then we get minus zt w tilde 1t theta 1 dw1t, that is this term here. Then the next term, minus w tilde 1t zt theta 2t dw2t, that is connected to this term. And then we have in this, we have a mixed term that cancels out at dw2t dw1 that's equal to 0. dw2 dt is also equal to 0, so this one cancels out. This one times the last one cancels out, and the only one that remains is the dw1t times this term here. So that is minus ct theta 1t dt. Remember dw1t, dw1t, that is equal to dt. So that is what remains. And then we see that the dt term cancels out, which we typically like when we look for martingales and Ito processes. So that term cancels out. And in the end, what is left, if we take a zt out of brackets, it is zt1 minus theta 1t w tilde 1t dw1t minus w tilde 1t zt theta 2t dw2t. So we see a term with dw1 and a term with dw2, no dt terms. So this is our favorable formulation. So we conclude that what we see is a sum of two Ito integrals. And because we have two Ito integrals, we know that the product w tilde 1t zt, where 0 is less or equal to little t is less or equal to t, is in fact a martingale under P. So that's a good, and we get the same, of course, for w tilde 2t times zt. We do that in a similar way, and we also see that that is a martingale under P. Now, the next step, then we use lemma 5.2.2, and by lemma 5.2.2, we get that for time s less than time t, that we have the following, the expectation under the P tilde measure, again, remember denoted by the expectation sign with a tilde up front, of w tilde 1t given the filtration up to time s, that is in case of, with the help of lemma 5.2.2, that is 1 over zs, the expectation of w tilde 1t zt fs. And now we know that this is a martingale. So we know that this conditional expectation is in fact equal to w tilde 1s zs. Then the zs cancels out, and we have what remains is that in fact we see that this is in fact a martingale, because under the tilde measure, because the expectation under P tilde of W1 tilde T, given the filtration of, up to time S, is in fact W tilde 1S. And the same we find for W tilde 2T. So in other words, for both I is 1 and I is 2, W tilde IT is a martingale under P tilde. And then with the Levy characterization, having confirmed the last property, the fact that we're dealing with martingales, we can conclude by means of the Levy characterization of Brownian motion that the vector W tilde T, consisting of W tilde 1t and W tilde 2t, 0 less or equal to little t less or equal to t, is a Brownian motion under P tilde. Quod et demonstrandum. All right, what is the next step? The next step in our section is theorem 5.4.2, and there we generalize the multidimensional martingale representation theorem from last lecture, and we generalize it to 2 dimensions or multiple dimensions. And how did that go? Remember that we had a fixed time capital T, and we assume a filtration Ft T between 0 and capital T, and we assume that that is generated by the d-dimensional Brownian motion. So we have our vector value Wt, and that consists of W1t, W2t up to Wdt, our d-dimensional Brownian motion. And that was a special filtration. You remember, it is a filtration, the script Ft, that is a filtration that is in fact the smallest sigma algebra contains all the information. So it is WS, where 0 is less or equal to S is less or equal to T. And now let M be a martingale. Again, we stay in our time 0 to capital T. Let that be a martingale with respect to that filtration, script F, and that special filtration, and under P. Yeah. And then we say in the multidimensional martingale representation theorem, we say that there exists a gamma. Then we say there exists a d-dimensional adapted process gamma, consisting of gamma 1t, gamma 2t, up to gamma dt. Again, little t between 0 and capital T, such that mt, our martingale mt, is equal to m0 plus the integral from 0 to t of the inner product of gamma of vector gamma u times vector dwu. And if we write that out into components, it says it's equal to m0 plus the integral from 0 to little t. The sum I runs from 1 to d, gamma iu dwiu. So a sum of these terms. And what now? Well, you see that this is in fact the multidimensional generalization of the one-dimensional martingale representation theorem. And what this theorem tells us is that if we are dealing with a martingale, there exists a gamma, there is a gamma, so that this formulation is valid. That is what it basically means. Moreover, remember, this is all under measure P, and under measure P, and dwu and dwiu, it's under measure P with this filtration. And we also want to have a similar thing under measure P tilde, under the risk neutral measure. So if P tilde is the risk neutral measure, and then given by Girsanov's theorem and the fact that M tilde T is a martingale under P tilde, but with respect to the filtration ft, not yet f tilde t. And that was that little technical issue. So if P tilde is the risk neutral measure, then we can also write m tilde t as m tilde 0 plus the integral from 0 to little t, gamma tilde u d w tilde u. And that's an inner product here. Again, that's an inner product of two vector valued functions. So we see that when we're under the risk neutral measure, then again, if we have a martingale under the risk neutral measure, we can write it like this with a vector valued process gamma tilde u and a vector valued process dw tilde u. And that is part of this representation theorem. But here is that technical detail. So we say that there exists an adapted process. It is with respect to f, that process is with respect to f, but we can write the martingale with respect to f tilde. Note that w tilde t is wt plus the integral from 0 to t theta u du. It's a it's a vector equation. And what I meant with the technical detail is that we are dealing with the wrong filtration. When we apply the martingale representation theorem, we are dealing with the wrong filtration. We have this f here, but we are working with f tilde when we are looking into it, as in the one-dimensional case. And the steps in the proof that resolve this are again in exercise 5.5. And basically the steps are the following. We define mt is zt m tilde t, and we show that mt for little t between 0 and capital T is a martingale under P. That's the first step. And that's the first step. The second step then is we use the martingale representation theorem on mt. So we write mt as m0 plus the integral from 0 to t gamma u dwu, where this is again an inner product. So this is vector valued. This is an inner product, where gamma u is adapted to the filtration ft, and little t again between 0 and capital T. And finally, we write m tilde t as mt divided by zt. And then we can use the Ito product rule. We can use the Ito product rule. We write dm tilde t as gamma tilde t dw tilde t, and we integrate to get the result. And again, by working this out in exercise 5.5, we see what we mean, what we mean, and this is essentially the same as in 1D. Well, this concludes section 5.4.1. So we have now finalized the description of the Ito of the martingale representation theorem in 2D. And thank you for your attention.